This is Design Safe Radio, where natural hazards researchers strive to make our society more resilient to everything nature throws at us.
Hey, hello, and welcome to another episode of Design Safe Radio. I'm your host, Dan Zahner, and with me today we've got Dr. Ben Schafer, who is the William and Lillian Hackerman Professor of Civil and Systems Engineering at Johns Hopkins University. Ben, it's good to see you.
Yeah, it's great to be here.
Give us just a 60-second intro about yourself and a little bit about your research before we dive into the deep end.
Yeah, sure. So Ben Schafer, I've been a professor at Johns Hopkins for 24 years. I worked in practice at Simpson Gummerson Hager for a little while and still have a consulting relationship with them. And, you know, back long before that, Cornell and all those good times at the University of Iowa as a student. But I've been working hard as a structural engineer, primarily in steel structures for my career.
Excellent. So a lot of us, people in our audience, they might be familiar with how concrete buildings are constructed or wood frame structures and how those can be seismically resilient, but not so much with steel, like the red iron steel that we see, riveted together, welded together, or cold form steel or CFS, which is what your research focuses on. So can you talk a little bit about, you've been at this for over a decade, but even back to before NHERI was a thing and back to the NEIS days. What is cold form steel? Let's start with that. I'm a mechanical guy, so we got to start with the material.
Sure. Yeah, awesome.
Then we'll go into how it's used.
Yeah, so cold form steel, in comparison to hot rolled steel, is just a designation of the actual shape that the structural engineer specifies is cold bent into that shape. There's a number of processes for doing that. The more important thing to kind of understand is like you can make steel from sheet and coil. If you do, you're making cold form steel. You can make steel from plate and bar and shape, thicker things. That's generally going to be hot rolled steel. And so as a structural engineer, you sort of start out with, I don't know, you got like 2 millimeter thick steel or, 68 mil still, and depending on how you want to talk about it or whatever, it's pretty thin, right? And so what am I doing that as a structural engineer? So turns out you're doing a lot with it. Already today, large percentage of all the rack structures that are used in warehouses, all the secondary system for metal buildings. And then over the last 40 years or more, a growth in direct cold form steel framing. So started out pretty much mimicking timber, kind of stick style, replace a 2x4 with a 2x4 thin steel bent shape. Grew quite a bit in non-structural, just splitting up the walls. You'll see it in a lot of mid-rise and high-rise construction now, the non-load-bearing walls using light gauge metal, another word for cold form steel. But my primary interest has always been in when you want to use it for the structure. So you want to carry the load, stop the wind and the earthquake, provide a safe and resilient structure. But pretty much you're going to use sheet steel and, probably not more than 2 millimeters.
Yeah. Well, and some of the key differences of that is, as you talked about, is the wall thickness of whatever the final shape is. But also you go down to the microstructure of the steel itself is different than a hot rolled product and makes it lighter, but has some different advantages and disadvantages to it. Can we talk about
absolutely.
that a little bit? Building material.
Yeah, right. And to kind of put a modern spin on it so you can kind of, people can sort of understand, like most people are sort of aware of the fact that their cars are just built from sheet steel these days. So it's just spot welded and often glued together little pieces of sheet steel to form the body of your car. We don't pay probably as much attention to it. We don't think about it, how much material advancement has gone into different steels that are used in different parts of your car. So the same way structural engineers, we want certain things to happen in our building in an earthquake. Mechanical engineers want certain things to happen in a car. And so there's a lot more variety in what you can get out of the ductility and strength out of sheet steels than you can get out of plate and shape.
Yeah.
So you can get materials that yield 3-4 times higher than what we typically use in hot rolled structural steel. You can get ductilities as large as you like, 40, 50%, or really
Wow.
small, depending on how you work the material. And so folks that work in sheet steel are kind of used to thinking more of the material as part of the design space. So it's not just steel, it's which specific sheet steel and what ductility and what strength do I want out of it. Like in a car, you might want right next to you in what they call the A-pillar, a lot of protection. So you might want a really strong cage or whatever, but up your bumper up front, like when my high school senior hit our Corolla against someone last week, I wanted it to dissipate a lot of energy. So it has
Yeah,
a sheet steel
exactly.
with high ductility. So, you pick and choose.
Yeah, and it's a lot different. Like it's funny you picked the car analogy. I actually used to work at a Subaru factory as a manufacturing engineer, and so saw a lot of sheet steel coming through.
Yeah,
But it's very different than like an old Land Rover and how, yeah,
that's
that's made
right.
from steel too, but it's plate, it's welded.
Exactly. So
That
that's that evolution in automotive is it parallels and leads kind of some of the evolution that you see that's been going on in cold form steel building construction for the last many years.
Yeah. And so this leads to now an advantage of the cold form steel in your research of how you can use those different ductilities, different elasticity, different strengths as ways to dissipate seismic energy and make
Right. So huge,
more
so you've got
stable.
this nice material design space. You can use different sheet steels, get different behavior. That's like the plus. The challenge, of course, is that you're choosing to use something really thin, right?
Yeah.
So the structural engineer has to own up to local buckling and other types of buckling limit states that occur inside that sheet steel and design, really incorporate them in their designs. And that's something that is very different, particularly when you start thinking about seismic and structural safety and resilience. So we tend to try to drive everything towards, particularly in the steel world, could I make it yield? Can I make everything go away except for this one thing that I want to have happen? Well, if you choose to build your whole structure out of 2 millimeter thick sheet steel, the local buckling is going to happen. So you have to decide, how do I deal with that kind of local buckling and also still get the energy dissipation that I want? So get it to happen in a certain location, in a certain way. So it's really, you have to up your engineering game a little bit to drive the behavior that you want.
Yeah, it sounds like if we got any electrical people listening in, it's almost making like a physical version of a fuse, so that you drive that buckling into a place that's easily replaceable, like a fuse, so that you can put that building back into service much quicker after an
Yeah,
event.
and that's been an important, kind of thought process for seismic structural engineers, and capacity-based design and those ideas, which really are really been important for seismic engineering and becoming more important for wind, as well as we deal with,
Yeah,
climate change and more challenging winds.
yeah, absolutely. So kind of walk us through what you've been working on since the Nice days and how that's kind of evolved over the years as we're getting into NHERI, and now we've got a really big cold form steel structure down
Yeah,
at
absolutely.
CSG.
I've been working on cold form steel since my PhD days, so 25 years
Yeah.
plus. And we're working basically in the early days on, could we make a better member for a person, right? So can we add a stiffener or choose the material a little bit differently? But the goal there was to maximize the strength, minimize the weight, pretty classic sort of objectives. And a lot of that work went into design specifications that engineers use. And that's kind of like phase one of my career, more or less, is, really focused on that. Um, since the Nice days, what we've been focused on is cold form steel being used in a system. What we found is our best calculations for the strength of like a relatively low-rise cold form steel building versus when we actually built one and tested it back in
Hmm.
the Nice tests at the University of Buffalo. The building was far stronger, far stiffer, and behaved much better than our sort of engineering calculation would have actually revealed to us.
Hmm.
And so that opened up this big puzzle of, okay, so this thing behaves really well. Why? Right? I mean,
Right. Yeah. Wait a minute.
what's it doing as a system that's different than what we expect as an engineer? And we start to really understand that the full building system, the cooperation between the structural and the non-structural, is a little different for cold form steel that uses repetitive framing than for reinforced concrete or structural steel that uses very widely spaced bays. And we sort of really only focus on the structural system. And so
Hmm.
working on that aspect has been a major part of the uncovering of how these systems really work for the last many years now.
Wow. Well, and on top of that too, it would glossed over another advantage of cold form steel is the sustainable nature of it as well.
Right. I mean, so cold form steel has two kind of major aspects to it, right? I mean, you're trying to decrease the mass, use less material. I mean, it is a from its inception, it is a material efficiency idea, right? Can I use the absolute minimum material? And that's a big sustainability goal in general, because the embodied carbon of every piece of material that goes in, you can't get rid of it. The other aspect of sheet steel and coil steel, particularly in the United States, is that most of it is made from electric arc furnace recycled steel. So the recyclable content of steel, particularly domestic U.S. steel in sheet and coil, is very high. And so it's one of the few places where we actually have a domestic circular economy. That is totally real. I mean, so when you throw away your stove and it's got sheet steel in it, it does not just go away. I mean, it makes it to recyclable and, makes it onto a train and gets an electrode stuck into it and turned back into more steel.
We need to find some videos of that to put in the show notes. That sounds
well, we should talk to some of our friends at Nucor and places that do that on the regular.
Yeah, absolutely. I mean, I could watch that for hours.
Thanks for listening to today's episode of Design Safe Radio. Be sure to like and subscribe on whatever platform you happen to be listening to this on. It really helps people find our show. Thanks to our amazing sponsors, the National Science Foundation and the NHERI Network Coordination Office, which is award number 2129782. Big thank you to Marty LaChance, our guest booker and topic researcher extraordinaire, and Raquel Ruiz, who is our video and audio editor. I'm your host and NHERI Facility Scheduling and Operations Coordinator, Dan Zahner. We'll see you in the next episode. Until then, stay resilient.